Welcome to Wildcat Science with Mrs. Haugo. This is Advanced Science in our water unit, and today we are exploring why is water weird? So, water is definitely weird, and let's talk about why that is. It doesn't seem weird to us because it is so commonplace, but water is a really weird chemical. The first reason it is weird is that solid water is less dense than liquid water. Make sure you wrote number 1 down, but you don't have to write down this purple stuff. So that is very weird that solid water is less dense than liquid water. The solid state of most things are much denser than the liquid state and will sink. Usually what happens when a solid is formed is that the molecules become more tightly packed together, and when things melt, the molecules move apart and they become liquid and can flow over each other. So water is really weird in that the solid state is less dense than the liquid state. And why is this? Okay, so let's take a look at this picture. So we can see ice, when it forms, has this really structured crystalline structure, and you can see that the water molecules are locked in place with other molecules because those hydrogen bonds make kind of freeze in place, and they make that crystalline structure, and they actually push themselves apart a little bit more than when they are liquid and can just flow over each other, and those hydrogen bonds are breaking and re-breaking, and so they actually get a little bit closer. So frozen water is less dense than liquid water, and that is weird. So please write this part down. Water expands as it solidifies into ice because molecules are locked into a crystalline structure where each molecule makes hydrogen bonds with other molecules. And the hydrogen bonds in ice keeps molecules a certain distance apart. But in liquid water, so liquid water has hydrogen bonds, but the hydrogen bonds are broken and reformed so those molecules can get closer together. I would like you to ask yourself, what is the implication of solid water being less dense than liquid water? And we'll talk about that in class. A second reason water is weird is that it has a very high specific heat, which means it takes a lot more energy to heat it up than other substances. So water has a specific heat of 4.18 joules per gram degree Celsius, and you should be gasping, it's so high. So put water in a metal pot on the stove. You can burn your finger on the pot, but the water inside is lukewarm. So please write this example down and then think about it. So you put a pot on the stove, and then if there's nothing in it, you touch it, you burn your finger. Whereas if you put the pot on the stove and in that same 2 minutes, you put your finger in the water, it wouldn't feel really hot at all. So why is that? Well, they're both getting the same amount of heat, but the metal has a very low specific heat, so it heats up really quickly, and the water has a very high specific heat, so it takes a lot of energy for the water to heat up. So let's look at a table of some specific heats. Okay, so you can see that air has a specific heat of 1, water 4, so that's 4 times. It takes water 4 times as much energy to heat up as air. Aluminum, steel, silver, those are all very low specific heats. Oil takes more energy to heat up oil than air, but less than water. And concrete, glass, gold, also, and wood takes a lot of energy to heat up. A lot more energy to heat up water than any of these things. Why does it take a lot of energy to heat up water? So please write this down. Energy must be absorbed to break hydrogen bonds, and water has a ton of hydrogen bonds. So if you're going to, let's talk a little bit more about the why. So please write this down. When energy is added to water, most energy is used to break the hydrogen bonds, and a little energy is used to increase the temperature. So you know they've got those hydrogen bonds, and whenever you add energy, you're using that energy to break the bond. But that doesn't actually heat up the water. So just a little bit of the energy goes into heating up the water. So when energy is added to water, most energy is used to break hydrogen bonds, and a little energy is used to increase the temperature. And then we know that temperature is actually the average kinetic energy of the molecules in a substance. So that makes the molecules move faster if you have a warmer sample, if you have water at a higher temperature. The molecules are moving faster. So in short, most of the energy goes to breaking the hydrogen bonds and very little of it goes to making the molecules move faster, which makes the temperature increase. So I would like you to ask yourself, what is the implication of water having a very high specific heat and for it to take a lot of energy to heat up water? And we will talk about that in class also. A third reason water is weird is that water has a very high boiling point for the size of its molecule. So compared to molecules of the same size, water's boiling point is very high. And so let's take a look at some boiling points. So water has a molar mass of about 18 grams. And so all of these, most of these are heavier molecules, and therefore you would think that it would take more energy, or they would have a higher boiling point because it would take more energy to get a bigger molecule to heat up. So diethyl ether, it will boil at about 34 degrees Celsius. Acetone, found in nail polish remover, at 56 degrees Celsius. Methyl alcohol, also known as wood alcohol, that will boil at 64 degrees Celsius. And then ethanol, grain alcohol, alcohol that's in alcoholic drinks, that has a boiling point of 78 degrees Celsius. And then water, which is the smallest of those molecules, is at 100 degrees. So I know this seems normal because we grew up with, that's the temperature that water boils at. Water is so common, but that's a really high boiling temperature for the size of its molecule for being a covalent compound. Why? Why does water have such a high boiling point? So to become a gas, all the hydrogen bonds in water need to be broken. And we know that water has a lot of them. So please write this down. Water has lots of hydrogen bonds, and it takes lots of energy to break all those hydrogen bonds. So after you've written that down, you can make this picture, but you don't have to. So you have solid water, which is ice, and you can see it has this very structured structure. And so those hydrogen bonds are kind of frozen in place. And then in liquid water, those hydrogen bonds are forming and reforming and it's flowing over each other. And then in gaseous water, the molecules are zipping around and they are not connected to each other at all. So to go from liquid water to gaseous water, which is what happens at the boiling point, you have to break all of these hydrogen bonds. And there's a lot of them, so it takes lots of energy, so water has a high boiling point. So I would like you to ask yourself again, what is the implication of water having a high boiling point? And we'll talk about that in class. A fourth reason water is weird is that water has a very high freezing point for the size of its molecule. So I'm going to tell you something amazing. Water freezes at 0 degrees Celsius. Okay, so compared to molecules of the same size, water's freezing point is actually very high. That's what we know, and water's very common, so it doesn't seem weird to us, but it is. So please write these things down. If water was normal, it would be a gas at room temperature. There would be no ice and no liquid water. There wouldn't be any living things on Earth because all living things need liquid water. So water is the only substance naturally found as solid, liquid, and gas on Earth. So please write those things down. You don't have to write down this table, but please pay attention. So water has a formula or molar mass of about 18 grams, and it has a melting point or freezing point. So melting point and freezing point are the same thing. Melting point is when something is going from solid and melting into a liquid, and then freezing point is when something is freezing, going from liquid to solid. So same temperature. So something that has a similar molar mass, ammonia, will melt into liquid ammonia or freeze into solid ammonia at -78 degrees Celsius roughly. Something with another similar molar mass, methane, is solid at a -182 degrees Celsius, and methanol would be solid at almost -100 degrees Celsius. And that has about almost double the molar mass. Ethanol has double to triple the molar mass. Carbon dioxide more than double, and those two freeze at -117 and -50, about -60. And then sulfur dioxide, which is like triple, freezes at about -70 degrees Celsius. So you can see that these all freeze at very low temperatures. So we never find these naturally in the solid state on Earth. But we do find solid ice on Earth. Why? So a substance freezes when the molecules stick together, and those are the intermolecular bonds. So you have two molecules, and then you have a force of attraction between them, and when that force of attraction kind of sticks them together, then it stays in a solid. And that's when we say it has hit its freezing point. And water has lots of hydrogen bonds, which are a type of intermolecular bond. So as the molecules slow down, which means they have become lower in temperature, they have less kinetic energy, the force of the hydrogen bonds overcomes the kinetic energy of the molecules, and those molecules stick or freeze in place, and then our water has now solidified into ice. So this happens actually at a very high temperature. So and it's really easy for water to become solid ice compared to other small molecules like carbon dioxide, which happens at about -60 degrees Celsius. So what is the implication of water having a very high freezing point and for it to be easy for water to be solid on Earth? Okay, we're going to pause there. In our next video, we are going to look into why water is weird, because it can move against gravity. I will see you then. Bye.